Hello, my name's Joel Shaw. I'm with Silverwell. I'm the VP of Products. And just a quick history of myself before we get started. I've been in the industry for about 20 years, well, more than 20 years now. Started doing BOPs and worked my way through a bunch of different things from mud motors, wireline intervention, and all the way up to through intelligent completions. Now, lately, I've been focusing on gas lift, which I find fascinating. It's been around for a lot longer than I have, and developments are still happening every day, and I'm excited to be a part of this next revolution with surface controlled gas lift. Title of this paper is Quantifying Greenhouse Gas Reduction Estimates for Surface Controlled Gas Lift. And really, so just to give a brief introduction on that, in recent years there's been a big drive to reduce greenhouse gas emissions across the whole oil industry. Uh, it's important for us to understand how these emissions are affected by what we do as operators and managers of these resources. What I'm going to be talking about is surface controlled gas lift and how that is giving us the ability to monitor, control, and make changes to downhole gas injection. Now, this has a real effect on production as well as emissions, and I'm going to go through some of those and discuss how those effects and build a model quantifying them as this proceeds towards the end, and then show a case study of what that looks like. So the agenda. This is a brief outline of what we're going to be talking about. Uh, Key point is throughout this is that greenhouse gases can increase or decrease based on production decisions that the operator makes. Carbon intensity is a method that's used to kind of normalize the amount of emissions per oil produced. And I'm going to show that using some very basic information about the well, we can determine how decisions made on a well from a production standpoint, gas injection standpoint, change that carbon intensity. This is very much not vendor specific. This is meant to be for surface controlled gas lift optimization. It's even applicable to, for instance, if you put foam in a well. But it will be more focused on gas lift. To me, the point with this whole thing is to better understand how our decisions and the decisions we make on a well impact the world around us, and namely greenhouse gas emissions. Just kind of a layout and agenda we're going to talk about. Initially, carbon intensity is going to be defined. That's going to be followed by a description of surface controlled gas lift, how it's used a little bit to optimize wells, and how that affects carbon intensity. Again, somewhat generic based on manufacturer. Then I'm going to show some assumptions and use those basic assumptions and some basic calculations to go through and derive some equations that'll kind of show how some basic stuff on the well can be used to determine what the change in carbon intensity is going to be. And finally, some results will be presented. Okay, first, it's important to define carbon intensity. Different parts of the industry define it differently. Midstream, that's the amount of emissions created while transporting oil or gas to the final destination. Downstream, it would be the emissions created from refining. Upstream, it really relates to the CO2 emissions created during oil production, and that's lifting from the reservoir up to the surface. We'll use the mass of CO2 in kilograms created to produce each barrel of oil equivalent for our definition, and I actually have that written out in the next slide or one or two later. The point is carbon intensity is indicative of what the carbon footprint is, and higher carbon intensity means more greenhouse gases are created. There's a couple ways to reduce carbon intensity, and that's either create less emissions for the same amount of oil produced, or increasing the amount of oil with the same amount of emissions, or a combination of the two. So let me go on. Surface controlled gas lift. So this is just some basics on surface controlled gas lift. There's really two main types right now, and that would be electric and hydraulic. There's some advantages of each one, and I'm just going to touch on the surface on this. But electric offers you more control. You can better control what the injection rate is. You can more easily get surface readings. You have less lines of the surface. However, it is more susceptible to small leaks in the control system. For instance, if you have a tiny pinhole leak with a hydraulic system, you might never know it. If you have it with an electric system, eventually you're going to flood the system and have problems. Hydraulic systems, very well proven. It's been around years and years in the industry. Most of them require more than one control line. ICVs in the industry is a typical case where it's become well accepted. It does require a more complex surface system, and there's less functionality when it comes down to being able to more accurately control position, what your injection rate is, get feedback from downhole, or include gauges. That would require a separate line. Typically for hydraulic lines, sometimes you'll have one line, but typically there'd be two, or N+1, where n's the number of nodes. There's other places that go into more detail on what those look like, but that's not the purpose of this paper. I just wanted to mention here what some of the things out there are, and the calculations that we're going to be moving on to are relatively independent of these numbers, or of the type of surface control gas lift system that's being used. So, to summarize, here's the equation that I'm using for carbon intensity. It's CO2 production, which is the amount of CO2 created while you're, in the case of gas lift, it's mostly due to compression services. So compressing the gas that will be injected, divided by oil production. So if you want to decrease a number such as carbon intensity, and it's a fraction, the choices are to either decrease the numerator or increase the denominator. How can you do that? Some of the ways to do this are better gas placement. In the situation of gas lift, that means injecting gas deeper. It also means better gas utilization. That means putting gas to the wells that require it in the most optimal way. Using all the pressure you have available at the surface, so you're not, or at the surface downhole, so you're not dropping the pressure with a surface choke. Not multi-pointing. Optimization, making sure that you're not over-injecting, not under-injecting. And yeah, that's, I mean, just some of the things. As I go on, I'm going to show how you can estimate this carbon intensity number using some basic information that can be supplied by any gas lift vendor. So, what is this not? This isn't a way to calculate absolute carbon intensity values. For any given well, there's too many variables to do in a very simple way. You can do estimations. But one of the big things is, where's the energy coming from, right? So if you have solar energy or, say, nuclear energy, there's little greenhouse gases created. If you're using coal, there's a whole lot of them, and there's all kinds of other choices. It could be hydroelectric, could be natural gas, it could be on a mouse on a treadmill. But the point is, there's too many variables to understand to calculate just in a basic across the board set of calculations like I'm going to present. The other thing is that this does not include estimations of energy required or carbon intensity for things like rig moves, workovers, things like that. We've done some numbers and looked at them, and those are relatively small to the ongoing CO2 emissions from compression services. So that's not included in here, but that does make this a more conservative approach, because one of the big advantages of surface controlled gas lift is that it gets rid of a lot of those things like rig moves, workovers, especially offshore, where those can be very, very carbon intensive. What this is a way to quickly determine how changes an operator makes can affect the overall carbon intensity based on the ongoing compression services. So, assumptions. And there's just really a couple main assumptions. One of them is that CO2 production is linear with the amount of gas compressed and subsequently injected. So that being said, it ignores some things like changes in infrastructure that might happen if you need less gas. It's kind of independent of the type of gas or the amount of gas produced, because, well, it's being compressed and re-injected, and that's how these work. The other thing, again, as I mentioned before, is it ignores ongoing or CO2 due to things like workovers, rig time, because again, as I mentioned before, this is insignificant compared to what the ongoing CO2 injection or create CO2 rejection from the compression process, and it does make for an overall more conservative estimate. Okay, variables. Here's a list of the variables used in the derivation. A lot of them are there just to kind of convert things from percentage or ratios and things like that. They're all pretty basic, and like I said, a lot of them cancel out. There's just a couple that are needed at the beginning and end. If you'd like more details on some of these, we can discuss it later. There's also on Silverwell's website a white paper that goes through this. So you can contact us or search our website for that white paper. But either way, it'll get you some more details on both this and the calculations, or well, calculations and the derivations coming up. So here's the initial equations that we have to work with. These are mostly just basic equations, efficiencies and ratios, simple division, multiplication. I'm not going to go through all these in detail. There's much more detail in the white paper if you want to look at that, or feel free to contact anyone at Silverwell, and they can answer it or get with me. Here's a derivation. What this does is it's the derivation of the percent reduction in carbon intensity. It's all just basic algebra. Forgive me if I called some of the steps in this derivation the wrong thing. I'm not a math scientist. I'm more of a mechanic than anything. But important thing is at the end, this shows that the percent reduction in carbon intensity can be estimated based on a couple basic things, such as the increase in production and the reduction in injection gas. Now, any service provider that's going through and doing a well for any operator should be able to go through and model the reservoir, model what the difference in production is going to be, what the optimized gas lift is, and how that optimization might change over time, what the advantages are in production, reduction in gas injection, and then calibrate those models using the surface control system downhole gauges to give you a better estimation, better understanding, and keep improving that process over time. Another advantage of the surface control system is you can make those changes instantly without required workover or anything like that. This is another derivation. This shows if you know what the initial carbon intensity is, and then if you increase production or reduce gas injection, what that does to the overall carbon intensity and what you end up with. This is helpful if you already know from a baseline what wells, what the carbon intensity is, or you can also calculate if you know what the total carbon production is and overall production. But it gives you a way to quickly go through, understand when you're making a change to a well, or when you have made a change for a well, what the reduction in gas injection and production will do to the overall carbon intensity. So this is a heat chart showing just what those percentages look like. When you reduce injection, when you increase production, you can use this to look up where that puts you from a carbon intensity reduction standpoint. It's kind of interesting a little bit to me to see that the sum of both together can be much more than just one. For instance, if you have, say, 20% reduction in injection and 20% increase in production, you get 33% overall carbon reduction. And also it's not doubled. There is some correlation of both of them and how they model together. But the important thing, again, in practice, is to be able to make production decisions, understand how it affects the environment, understand how that affects the overall field carbon intensity, and understand what the ramifications are. Will it always be a situation where changing the gas injection and increasing production increases or improves, so reduces the carbon intensity? No. Sometimes it can go the other way, but the operator needs to understand how those decisions affect those greenhouse gas emissions. So now on to a quick case study. So here's a case study of a well that was actually in Bahrain. There's a case study on our website about this that you can look at. I don't think it says Bahrain, but we can point out to you which one it is. But what we did is we went back and applied these calculations to see what kind of carbon intensity reduction is. This one actually had a pretty significant carbon reduction. Again, not all of them do. Some case studies would even go the other way, where the carbon intensity increases, but there is tremendous increase in production. So the operator, again, has to balance that stuff. But in this particular scenario, it's a very simple completion. There's only one dial unit in it, so one surface-controlled gas lift valve. But what it did is allowed the operator to see what's going on, understand the well, understand the ramifications of what's happening when they make changes, and how that affects production, how that affects the amount of gas injected, and really what the greenhouse gas emissions are. Using the sensors, they were able to tell and do some calculations and determine that they were actually over-injecting. So over-injecting, in that scenario, you're injecting too much gas. That causes a restriction in production, and that means your overall production's reduced. So you don't have as much drawdown as you would have otherwise. You're wasting compression services. That gas could go to other wells and be used to lift over there. So it's just an overall bad situation, which you can't really see when you just have gas lift valves, or conventional gas lift valves, because you don't know exactly what's going on. So in this case, they were able to get an 18% increase in production, while at the same time reducing gas compression, or the amount of gas injected, by 25%. So overall, you can see on the chart here, and I have it blown up, that yielded a 36% reduction in carbon intensity. Again, this is one of the better examples. Sometimes it's not like this, but sometimes it's more. So it just really depends on what that particular well looks like, the situation of that well, and that changes over time. With conventional gasless systems, you're not able to quickly make those changes. You can't go in without intervention. You can't adjust it, see what it does, and then adjust it back if you went the wrong direction. So this allows you to do all that real-time optimization, real-time decisions on the amount of carbon you're creating, the amount of production you're making. If you want to limit production on a well and do it in an effective manner, not wasting the injection gas, you can do that. So this is a great example of that. Okay, so now I'll move on to conclusions. Just some basic conclusions are listed here. And really, with surface control system, you can use modeling, real-world results to optimize what those models looks like, and really determine what production and gas injection is going to look like for various scenarios, for various changes in the wells, and make those changes, verify them. If it's not, update the model. This information can be utilized to both understand the ramifications and the trends related to emissions, and how changes in gas injection and production affects carbon intensity, and make informed decisions moving forward, and plan better utilize what those compression services are, what the infrastructure that's in place. And to expound on that, surface controlled systems give the operator the real-time ability to make those changes and tweaks, move them a little bit, see what it does. And these calculations, using the information from that, lets the operator make informed decisions about greenhouse gas emissions, production, how those two play together, and do all of that real time. I've kind of gone through this quickly. I just barely touched on the surface of a lot of it, but every bit of this and more is, again, on our website. It's published as a white paper that goes through and goes some of the detail about how these were derived, some of the assumptions made. That might be revised as we make more updates in the future, but I really hope that this gets used, and even if it's modified, it gives some ideas, or creates ideas of how moving forward we can better utilize these to make better decisions. I'm going to move on to acknowledgments, and I'd really like to thank the ALRDC for this opportunity to pull this together. I've presented this prior to this, but this is something that can be looked at, can be viewed later on. People can come back and look at, and it will be just an opportunity for more people to see it that can't make it to the presentation. And again, this is not meant to be specific to any vendor. This is meant just to build on the industry so that we can create a better world moving forward. Silverwell, I'd like to thank for the opportunity to be part of some of these developments and really pushing the industry towards another level in gas lift. And man, the industry as a whole, that's kind of an odd one, but it has continued moving forward to make strides to improve production, produce more with less people, less intervention, reduce carbon emissions. It's a different industry than it was when I started 25 years ago, and a hugely different industry than what it was 50 years ago. And it just keeps getting better, safer, societally, more proactive from an environmental impact, much better. So thankful for that. I mean, and you know, it's our world, but it's also our kids' world and our children's world. So it's really neat to be a part of that moving forward. Now I'm going to go on to some of the legal stuff. Here's some copyright information. I'll leave it here for 12 seconds or so, and then I'll move on to the next slide. Okay, I lost count. I don't know if that was 12 seconds, but you can hit pause if you want to see more of it. Disclaimer. Wow, this one probably will take 23 seconds, but I'm not going to wait that long. Again, you can hit pause. It's again, thank you for watching. Thank you for listening. Please get with me at Silverwell if there's anything I can answer further, or if you have any comments, questions, suggestions. Thank you very much. Have a great day. Goodbye.